We're going to do our last lesson for this unit that covers percent yield. So let's bring up our summary note. You have access to this, and there are 3 questions that we want you to answer. And these are based off of the formula to calculate percent yield. So percent yield is a comparison of the actual yield in a reaction versus the theoretical yield. And what do those terms mean? Well, it's very specific. And if you work through the summary note, you can read through and see what each of those terms represent. We'll review those in a second when we get to the Jamboard. There are 2 examples here that we're going to do together. And then there are 3 examples that I want you to try on your own. And percent yield is dealing with the amount of a product that we obtained. So a yield is indicative of how much of the product we will make or we will obtain. And we want a high yield. Okay, so we want that value to be close to 100%. And this is our formula when we are dealing with percent yield. So if we just set up our pen here, percent yield is equal to the actual yield divided by the theoretical yield. And what do these terms mean? Okay, we also multiply by 100% as well. So what do these terms mean? Well, theoretical yield is a fancy way of saying that it is the mass of product obtained through stoichiometry. So us doing some stoichiometry and mole ratios and coming up with amounts of a product is the same thing as saying that we are dealing with a theoretical yield. An actual yield has to be given to you. Okay, so it's got to be given to you, and it is the amount of the product that we actually obtain in an experiment or a lab setting. So while we do these questions, they have to give us an actual yield. We're not carrying out these experiments ourselves, yet we are supposed to compare that actual result versus the theoretical or the calculated result that we need to get. So as we start to do some of these questions, it's important that we understand the difference between the masses that are given. So here is an example. It says, consider the synthesis of aspirin. Okay, aspirin is a painkiller. Some of you might take aspirin. If you don't take aspirin, maybe if you need, if you have a headache or you got some soreness, you might take Tylenol or ibuprofen or Advil. Those are all pain relievers, but aspirin is a type of pain reliever as well. So here is your formula or your reaction to make aspirin. And the good news is it's all a 1-to-1 ratio, so we don't have to worry about balancing. And they tell us that 150 grams of acetic anhydride, which is right here, okay, so this is my reactant, reacts with excess salicylic acid. So we don't have to worry about a limiting reactant problem here. And they say calculate the percent yield if 252 grams of aspirin is synthesized. So my aspirin compound is right here, okay? And so this 252 grams is the actual yield, okay? So see how they're giving you that value because we're not carrying out the reaction ourselves, but somebody is. And so we need to know, well, how much aspirin did they actually obtain? And so what we're going to do is we're going to calculate the percent yield of this reaction. So we have to calculate the theoretical yield, okay? And remember that the theoretical yield is just a fancy word for the mass of that product, okay? And I know some of you are like, well, you just gave us the mass of that product. It's 252 grams. Well, that's the actual yield. So they carried out this reaction. That's what they actually got. when we do our 3-step stoichiometry, we should be able to figure out how much aspirin we should have obtained if everything went perfectly. And so we start with our 3 steps. We know that we're starting with 150 grams of acetic anhydride. So we're going to set this up. And as usual, we need to solve for moles. I'm telling you folks, when in doubt, solve for moles. Okay, so C4H6O3, we're going to take mass over molar mass. We're going to take 150 grams. And we're going to divide by the molar mass of acetic anhydride. So let me just calculate that. You should be calculating with me. 4 carbons, so 4 times 1201. And we're going to add on 6 hydrogens, so that would be 6.06. And then we're going to add on 3 oxygens. So 3 times 16 is 48. I'm getting a molar mass of 102.1 grams per mole. So we're going to divide that out, 150 divided by 102.1 grams per mole, and I'm getting a mole value of 1.46915 moles. Okay, you should carry, like, again, 4 to 5 decimal places there, and then we'll round to 2 decimal places when we get to the final answer. So we want to move over here to our aspirin formula. And the good news is that everything's a 1-to-1 ratio. So you could set up a mole ratio if you want, but I'm fine if you just write due to 1-to-1 ratio, because that's what I've got. Then what we know is that the moles of aspirin, which is C9H8O4, is equal to the moles of acetic anhydride, so C4H6O3. And that mole value is what I just calculated up above, so 1.46915 moles. Then I'm going to do a third step, and I'm going to take those moles of aspirin, and I have to figure out the theoretical yield. So how much aspirin do I actually, should I be obtaining if this experiment goes perfectly? So we're going to set this up, and we're going to take moles times the molar mass. We know the moles, 1.46915 mole. And then we need to calculate the molar mass of aspirin. So we've got 9 carbons, 9 times 1201. We're going to add on 8 hydrogens, so that will be plus 8.08. And then we're going to add on 4 oxygens. So an oxygen is 16 times 4 is 64. I get a total of 180.17 grams per mole. And when I calculate the mass of that, I'm going to get 46915. I'm going to get a mass of 264.70 grams. Okay, so this right here is the theoretical yield. Okay, that's the theoretical yield right here. And my last step, step 4 in this case, is to come up with the percent yield. And the percent yield is equal to the actual divided by the theoretical, by the theoretical yield times 100. And I'm running out of room here, but that's okay. So we're going to take that actual yield that they gave us back up here in the question. So 252 grams, and we're going to divide by the theoretical yield that we just obtained, to 264.70 grams times 100 gives me a value of, so let me close, to 100, but not exactly. It never is. It almost never is exactly 100% because you lose mass along the way. Sometimes you pick it up. So I'm getting a value of 95.20 Okay, so 95.20% for the percent yield of this particular question. So you'll notice it's the same 3-step method, okay, that we've been using. But what's a little different now is we'll always be solving a mass of one of our products. Okay, they'll tell you which one, and you'll know because they're going to give you an actual yield, an actual mass of that product. And then using our 3-step method, we're going to calculate the theoretical yield. So what is the mass that I should be getting if everything happened perfectly in this particular reaction? So let's move on to the next question. And the next question is a little bit small here on the screen, but you have this on your summary note. This reaction here is the reaction of copper wire. It says immersed in a solution of silver nitrate. So what we notice is that here's our overall reaction listed here for us. And it says initially 0.58 grams of copper is placed in a solution of silver nitrate. After the reaction is complete, the silver is collected, dried, and then weighed, and the following mass data is collected. So they give us an initial and a final mass of copper. They also tell us the mass of silver collected. So right there, they want to know, so silver is our product, and this right here is the actual yield. Okay, I can tell because they are telling me a mass of a product right here that was obtained. So there's a couple things we want to do. Number one here, it says calculate the mass of copper that reacted. So let's just do that off to the side. So the mass of copper that reacted is taking this initial and final mass and subtracting them off. So we're going to take 0.58 grams. This is what we started with. We let it react for a bit, then it was done. We had 0.22 grams left over. So if we subtract those off, and I should not need a calculator for that, that's 0.36 grams is the difference. That's the mass that reacted. And I'm going to use that value or that amount of copper to figure out the percent yield of silver. Okay, so what this means is I've got to figure out how much silver should I have obtained in this particular question or in this reaction. I know how much I got. Let's just clean this up here a little bit. So I got 0.13 or 1.30 grams. That's my actual yield. I want to know my theoretical so that I can figure out the percent yield. So we're going to start to set this up, and we're going to first calculate the moles of my known substance, which is copper. And again, that's all I have info for. I know how much of that reacted. So we're going to figure out the moles of copper, and we're going to take mass divided by molar mass. So we have 0.36 grams, and we're going to divide by the molar mass of copper, which is 63.55 grams per mole. And again, you should always have your periodic tables handy so that you can follow along and double check my work. So we're going to take 0.36, we're going to divide by 63.55. I'm getting a mole value of 0.00566648 moles. I need to get over to silver, okay? So the only way you can move from one substance to another is to use a mole ratio. Okay, so I got to set up a mole ratio between those two. So let's set up step 2. My moles of silver is what I do not know. I got to calculate that based on the fact that I'm going to react 0.00566648 moles of copper. And then I'm going to equate that to the coefficients. So I have 2 moles of copper in my reaction. That should be created if I had 1 mole of copper. Sorry, I think I said 2 moles of copper, 2 moles of silver, if I had 1 mole of copper. So we're going to cross multiply this by 2. And then the moles of silver that I get should be 0.0113297 moles. Now, I want to know the mass of silver that I was supposed to obtain. This is the theoretical yield. So I'm actually going to move down here and I'm going to calculate that. If you number your steps like that, it just makes it so much easier for everybody to follow along. So we're going to take moles times the molar mass. So my mole value is 0.0113297 mole. And my molar mass of silver is 107.87 grams per mole. And when I do this, I'm going to get, again, the theoretical yield. So how much should I have obtained of silver in the reaction? Okay. So I should have gotten 122. Just let's hang on here for a second. I'm going to double check my math. Okay, we're back here and we should have gotten a mass value of 1.22 grams for silver. And what we'll do is we'll take a look now at the percent yield. So we know that the actual yield for silver is 1.30. We should have obtained 1.22. So I obtained actually a little bit more than I should have, but that's okay. Sometimes that happens. And then what we'll do is we'll set up right here in this box the percent yield calculation. Actually, I'm going to move to the next one. Okay, so percent yield is equal to the actual amount divided by the theoretical amount that we calculated times 100. So we should have gotten 1.30, or sorry, we actually got 1.30 grams. We should have gotten 1.22 grams. And when we divide that and multiply by 100, we're going to get a value greater than 100%, but that's okay. That sometimes happens. Times 100%. So we're going to get a percent yield of 106.56%. And all that that tells us is that we collected more mass than we should have. And that can happen for a variety of reasons. Maybe there was moisture in your product. Maybe there were some, other products that you didn't wash away completely when you obtain that as well. So there are your examples of percent yield. Again, still just using the 3-step method. As we go back, we see here the 1, 2, 3 steps. The only difference is just some of these terms, okay? And then them giving you an extra mass of a product initially that will be the actual yield, and you calculating the theoretical yield of that same product in order to be used in the percent yield calculation.